My name is Juan Sequeda. I'm one of the founders of Capsenta. So we are a startup from spin out from the University of Texas at Austin in computer science. We've been doing our work on understanding the relationship between relational databases and the semantic web technologies. So semantic web based on RDF and OWL and Sparkle. This is Capsenta is very happy to share that we are a cool Gartner Cool Vendor this year. Only 5 companies in the whole world will do that, and as a startup out of UT, as a university startup, we're really excited to be there. So what we're doing is what we call semantic data virtualization. You're able to integrate your data without having to move it, have a semantic layer on top, and internally what we do is all graphs. So I want to share you a little bit of what we're doing, how we're doing it. But I want to start with kind of the big picture, the big problem. So I carry 2 hats. I'm a scientist by heart, but I also have to be in the field and putting on a sales hat and doing a little bit blah, blah, blah. But you really, talking to the clients and talking to the real people, you understand their real pain points. And it's really fascinating to hear the real problems and being able to figure out what is that translation into research and science. So the big problem we have in the enterprises is that you have the business people who have to make questions and do reports and generate stuff to increase the business, and all that data is in your databases. And there's this huge gap between the business and the IT, and the IT protects all this data. So here's an example of one of our clients, an e-commerce client, and the business users, they ask the question, how many orders were placed in the month of May, last month? So they go ask somebody in the e-commerce department, and they give a number. They go ask somebody in the shipping department, they get another number. They go ask somebody else in the billing department, and they get another number. Why? You would expect that this number would be the same. So really, they ask themselves, so what do you mean by an order? So an order for the person in e-commerce is when the user clicks on checkout. And if they ask the person in shipping, is when the customer actually received the product. And if they ask the person in billing, it's when the credit card got swiped. So what happens is that there is a lack of understanding. There is, first of all, the data's in different sources. There's an ambiguity, the data, what is the meaning of this data wherever it is located. There's no shared understanding for this, which means that there's a lack of semantics. So what is the status quo? What happens in the real world is that you have this business user who asks this question, right, what is the total sales of orders today? And they have to go talk to the IT person. And the IT person knows their database, or hopefully knows the database, so they start writing the query, but they may not know everything completely, so they have to go talk to the data architect, the person who created this, who knows the system and knows the business, and they figure out what it means, and then they go send some data back to the business user. Now, this business user gets data back from the databases, but they've also been doing some stuff with spreadsheets, and guess what? They have an access database where they put everything together, and they do more calculations there, and then they generate the report. So the data is being moved, the data is being copied. You really don't know exactly if you're getting the right results. And then, guess what? Oh, send me an update of that query that I sent you. So you get more data that needs to get updated all the time, and you have this one person who is doing it, and then you have this being repeated so many times. Now the question is, did the business user communicate the correct message to the IT? Right? Second, did the IT actually understand what the business user actually wanted? And finally, are the results that you're getting returned back, are they actually the right results? And at the end, you're making these decisions you may be making decisions on data you don't know if you're actually correct. So this actually happens every day. And I mean, as a student, right, you're looking into, you're studying all those databases and data integration, and you talk to people, and you see how they do stuff in the real world. At least for me, that was fascinating to figure out. And then you have this another status quo, which everyone was talking about, right? You say, well, I need to answer that same question. So what do people do? We need a data warehouse. So you have the data architect goes figuring out with the business people, goes figure out the database. They said, we need to integrate all these databases. So they come up with their enterprise schema that fits all their different databases. And then you have all the different IT folks writing ETL scripts to go move your data into your data warehouse. And this takes 6 months and $1 million. And they hate it. As you were saying, right? Go ask, I need another data warehouse. I don't want to talk to you anymore because and the thing is that they know that this is going to fail. So then the user can now be able to do their questions, and then you realize, oh, I need to ask another question, some extra information. But guess what? It's not in the data warehouse. So I got to go change the schema of the data warehouse. That means I got to go change the ETL scripts of that. And then things come back again. And it keeps evolving this issue. Now, imagine the IT person leaves. And they write these ETL scripts, which is code that who the heck understands what it is. So that's why it's this is why it's such a big pain. But this is how things work today. And even in the whole big data stuff, right? It's now ELT and stuff, but essentially, in 30 years, we still haven't changed the way how we are integrating data. Just think about it, it's still the same thing. Now, the other question is, I want to do cross-organizational data integration. So you were also speaking to that too, right? So not only in this organization do I have different databases, which by the way, they're different vendors. So I can't say, hey, Oracle talk to Postgres automatically, or in this other DB2 talk to SQL Server. I want to be able to do cross-organizational search, integrate data coming from different organizations. And these organizations are not going to release their data and create a warehouse. Not is it that they're just their own companies, right? Even within the department in a company, they don't want to move their data. And this is a big issue in healthcare. In healthcare, for HIPAA here in the US and stuff, you do not want to move your data. So how do graphs help around here? So I'm going to walk through this, but I'm going to give you an example, have a running example. And one of the examples that we have, which is, I kind of want to promote this a little bit, is the Constitute project. This is something that we did a couple of years ago, working with Google and a bunch of political scientists, where we created a search engine for the world's constitutions. So it was literally 200 different databases. Each database had very structured information about constitutions, one for each country. And what we did is that we helped them organize their knowledge about constitutions and integrate that all using RDF and OWL. And we have a search engine, and so you can search for all the world's constitutions. You imagine, why would I want to do that? Well, believe it or not, on average, there's 3 countries every year who rewrite their constitution from scratch. And there's around 25 countries who do amendments to their constitution. So people who write constitutions have never done it before, will never do it again. And they just want to search and find what happened, what other countries have to say. You can go check this out, and everything is powered by RDF and OWL underneath the hood. So I want to bring this up because that's a running example I'm going to be using. So graphs are cool. So why are graphs cool? One, they're flexible. This whole schemaless issue, right? I can just, hey, here's this node. This represents the Constitution, the U.S. Constitution, which was last amended in 1992, and it has some text. Here's this other node, which represents a particular part of the Constitution. It has some relationships. I can start building this graph little by little without having to kind of define beforehand all the entire schema. And if I have defined the schema, I can then just simply add a new edge and add a new edge that doesn't fit the schema, and things keep working. That's the really cool things about graphs. You have that flexibility. In a database, right, you have to, if I have to add something new, I gotta go alter the table, and in the real world, go ask your IT department to go add a new table to your database. It's gonna take weeks, if not months, to get authorization to do that. So, in addition to flexibility, you have integration. So, let's imagine I have this one graph, and then I have some other graph, which in particular is, for example, information that comes from DBpedia. It has information about the 8th Amendment of the U.S. Constitution and which Supreme Court cases are part of that. So I have 2 different graphs. How do I get 2 graphs into one? I just add an edge between the node. So just integration, if I represent data as graphs, integration of data becomes, we reduce the problem to finding edges between nodes. And what we've realized in practice, that's something that becomes a little bit easier to manage. Now, additionally, in graphs, data and metadata are one. So in a way, I can view this information as my instances, but I can also have information about my schema, right, the subclasses about how things are organized, and it's also represented as a graph. And I can now, all my data and my metadata, my data and my schema information are all represented in that same data model. In relational form, right, you have your relational schema, which is your tables and your attributes, and you have your data, which are the instances with data values in there. I can't query my schema. I can't say, hey, return me the table names. So that's something you can't do in SQL. I mean, there's a lot of work before the 80s and 90s about even schema SQL, right? That's even a higher order logic problem you have. Now, graphs are also a common denominator. So I can have XML information, which are tables. I can have text. I can have tabular information. And I can make a representation of all these different data models as graphs. So it's really a common denominator. So that's why you have different data sources. You can be able to integrate them if you put them all as graphs. So that's another reason why we think graphs are really cool. And then you can do traversals and navigations and reachability. We've been talking about that here all day. Now, with the semantics, right, you can actually say, you can have semantic information represented as ontologies here, as OWL and RDFS, and be able to infer new particular knowledge, which are also represented as graphs. So, to summarize, my personal feeling is that the reason why graphs are cool is because they're flexible. We can do integration very quickly. The data and the metadata are one. Common denominator, the reachability, and the semantics. Well, graphs isn't just a new thing. And I know somebody said it this morning. This is a great survey to realize the history of graphs, because this has been out there for a long, long time. And I really urge for people who haven't read this to take a look at it, right? We need to know our history so we don't repeat it. So the approach that we are doing here, and this is kind of the semantic web approach of doing integration, is that I have all my diverse data sources, and what we want is to have that target view of the world. This, what we call the enterprise knowledge graph, or the ontology, but this is how I want to view the world. Now, this is where the semantics come in play. When we were giving that example about an order, right, you want to organize what people mean, and regardless of where that information is, how it's structured, then later on what you want to do is that you want to create mappings to those things. So this particular knowledge graph, the good thing is that we have standards for that, which is OWL and SCOS. And then we want to create mappings from that target world that we're defining to the particular sources. And oh, by the way, those mappings are a standard, and they're also represented as graphs. So literally, the graphs is a very powerful data model which just helps us integrate their data. And then finally, we're able to create applications on top of this single layer, which in essence can be seen as our universal API. And guess what? We also have a standard to access that. So I think it's very exciting that we have these standards to be able to do this integration, all based on graphs. So I know it was mentioned a bit with the Oracle folks about mapping relational databases to graphs. They were talking about one of the standards, which I want to go through a bit because this is what we use underneath the hood. So in essence, what we want to do is that we have a relational database and we want to represent this as RDF. So if we have this simple database, we have a person table, city table, the ID is the primary key of person, CID the primary key of city, and there's a foreign key relationship between that. I can imagine that this would be the graph view of that relational database. Now the question is, how do I get from the left to the right? So there's actually standards from the W3C to represent those mappings. There's actually two parts. The standard comes in two parts. It's the direct mapping standard in R2RML, which is the mapping language. So in the direct mapping standard, it's an automatic, it's a default mapping, which takes as input the database schema and its constraints, and will automatically generate or can get you the RDF graph of that relational database. Obviously, it would be per the schema of how that's organized. So if you have a really nice normalized database, you'll get something pretty decent. But if you have a database without constraints or something that's completely unnormalized, then probably what you're going to get out of there is not going to be so nice, quote. But it's the first step of doing this, and this is a way of how to start the automation and bootstrapping. So there's a lot of rules about how to do this, and you can automatically get this information back. So you can get this graph back, and the standard provides rules about how to automatically generate the particular URIs and so forth. Now, this is just the first step, right? The next thing is to have this mapping language, which is called R2RML. And R2RML allows a user to define the mappings between a target, your target ontology, your target enterprise knowledge, which we call it, with your source database. And you represent these particular mappings. It's a declarative form because it's also represented itself as RDF. So the issue is that it's a new, basically, vocabulary language to write it. We don't want you to learn it. So what we do is that we've developed a lot of automated tools and systems to be able to manage all the mappings that you're creating and to automatically help you generate these things. So once you have these mappings, which represent the relationship between your data, your source database, and how you want to view the world, we want to virtualize it. So you want to take your source database, your relational database, and take SQL queries, and with the mappings, we want to be able to view that relational database as if it were a graph. But your data stays where it is, which means that I can run Sparkle queries in it, but I use the mappings to be able to translate the Sparkle queries to SQL queries and then return the results. So this is what a part of our system does. So at the end, when you're writing the queries, you're doing it in terms of the terminology that you agree upon, and you forget about how it's organized in the database, how it's called, and this is a separation between what the business folks want. They know this terminology at the target view, and once you create this mapping just once, and then it doesn't matter what is organized, how it is. And if something changes, your applications just keep talking that same terminology, and you don't have to worry about how things are organized in the bottom. So in an ideal view, right, in a completely virtualized view, you will have all your different databases. You create your mappings, and you're able to now view them all as different graphs. They'll all have your Sparkle endpoint, and then as Yevon was talking about, you'll be able to now federate Sparkle queries over all our different sources. But this is not one approach or the other, right? You can have some type of hybrid approach where you can say, you know what, part of my data I want it to be virtualized as graphs because this is data that for privacy reasons can't be moved or just gets updated all the time. But there's other data that's fine that I can actually move to a triple store. So I can now ETL it and keep another kind of copy, an RDF version of it, and now be able to view that also as a Sparkle endpoint, as RDF. And now I'm able to query and federate over everything together. So obviously you may ask, well, does this thing actually scale? Is this actually going to work? And Juan also mentioned about it. We were joking yesterday that we can probably exchange talks because we were talking about the same thing. And my point is, the scalability is not only about seconds. It's not how fast I can run this. It's the scalability per month. So if I need to integrate data and pull this all together, if it's going to take me 6 months and $1 million, or I'll wait a day or 5 minutes for a query, I will take that option. We have a couple projects where we do in healthcare where we need to identify patients. And they say it's for identifying patients who have pacemakers. There's 5 companies in the world who do pacemakers, and they don't share their data. So when somebody who goes into an ER room and they say, well, what is, they're coming in because they have chest pains, they don't know what pacemaker they have, from what brand, what company. So the nurse, what needs to do? He needs to get on the phone and call a vendor. They say, come over here. And they come up with a little wand at 3 o'clock in the morning. They go to the hospital and they go like this and say, doesn't work. Go call the next one. In the meantime, your patient is freaking out and probably dies. So it actually takes between 30 minutes and 3 hours to identify who this patient is. And they're not going to release their data, privacy reasons, and also competitive reasons. So if I have to wait 30 seconds or a minute or 5 minutes for a federated query, I'm fine, because it's going to take me 3 hours. A person may die. So that's the whole scalability of things that we need to understand. But the good news, and this is part of the research and stuff that we've been doing, and the stuff is that when you do the Sparkle to SQL translation, we have identified how to reuse the existing optimizations in some relational databases, which, oh, by the way, there's all this work on semantic query optimizations from the 80s. So when you actually take, in our system, if you take an English specification of a query and you give it to your Sparkle developer who writes the query, and then you give it to your SQL developer who knows the database schema, and you run them together, the query execution speeds are basically the same. And if you actually look at the query plans, and I think Oracle is actually the best on this, There's so many cases where we send them this gigantic query that the Spark or the SQL did because we know the database is going to optimize it, and the physical query plans are exactly the same. And this is just a view where blue is everything normalized with respect to the SQL database, and then you can have gray as what things happen on our side. And people who were trying to do this before would have orders of magnitude slower. So scalability is actually not going to be a big deal. It's going to be bigger when you're going to have a lot of the federation things, and there's a lot of details to think about there. But for this crowd, and the message that I want to leave is something that I call the tipping point problem. And it is, my starting point is a relational database, and I'm talking about graphs. When is the moment that I need to move from a relational database to graphs? And in my opinion, we don't know what that tipping point is. We're trying to understand what that is. So I have a problem, and the question is, can I solve this problem with the traditional relational database, or do I have to go to a graph? And there's a lot of excitement, there's a lot of buzz with the graphs, and people say, oh, I'm going to do this in graphs. And I've seen many times people who, at the end, they realize, oh, this actually would have been better and faster if I just did it in Postgres. So remember the reasons why I said graphs are cool? Flexibility. So if I have a relational database, an existing, and this is my assumption, I'm starting with the relational database, or a problem that I know that can be initially started with the relational database. I need to be flexible. I need to, I define a schema, and then I need to be able to add more things that maybe doesn't fit in my schema. To what point do I actually start adding more stuff that I really need to move into a graph? So you can think, well, I can have my traditional relational schema, and then I can put a triple table on the side. And anything that doesn't fit in the schema, I'll just stick it into the triple table. That can work, and I know people like Peter have been working on that. Up to what point does that scale, for example? I don't know. Or at least, probably Peter may have an answer now, but I think that's an issue that we need to consider. Integration, right? If we're going to do a complete, keep all our data in relational sources and virtualize them, up to what point will that federation actually scale where we say, you know what, it is better to just move it, have it physically stored in the same place, or have this hybrid approach? What is that tipping point? Data and metadata are one. Do I need to be able to store metadata information together with my data and be able to query it all together? Can I do that in a relational database or not? Again, common denominator, traversals. I think this one is really interesting, and I think somebody one of the talks earlier today was talking about it. You need to do a lot of recursion, and I forgot the talk on the benchmarks, on one of the benchmarks. When I looked at the paper, it was interesting that they were showing recursive queries. And so the data log system obviously worked well, and the Postgres worked for a couple of them, and it didn't work for the Sparkle one and for the native graph one. So databases can do recursive queries. How much of that can we actually push to its limits? And then we say, no, we got to move and do stuff in graphs, or be able to do when you're doing all these RPEs and stuff. Can we push that into a database or not? Up to what limit that we say we got to move to a graph database? And then semantics. I need to do inferencing. So how much of inferencing, subclass, subproperty, transitivity, can be pushed and be done by the relational database optimizer to the point that it says, no, I got to go find an RDF graph database that does reasoning. Part of my PhD work was a lot about semantics, of figuring out what was the right dialect of OWL, of the ontology expressiveness, that can be subsumed by the relational database and be done effectively. So to answer these questions, in my opinion, the overarching theme is to have a systematic and real-world benchmarks to evaluate all these different features. So that's why yesterday I was mentioning, I think it's really crucial that when we start, if you have a benchmark of graphs, give me also this relational version, because I need to have a base point. Because if I'm not, I believe that we are neglecting the work, the 30 plus years that already exist in databases. And sometimes you're doing things, comparing apples, and you're not really comparing the baseline that we are, which are the databases. Because again, it's happened many times. I think it works, but I realize I use a database, a relational database, and it works even better than doing stuff in graphs. So we need to understand this tipping point properly. So with that, I'll move into questions. Thank you very much.
Having spent the best part of 5 years of my life doing this in very large global banks and having built product to do this, I think the biggest problem comes right at the beginning. It's kind of the axiom that's being skipped a little bit here, because right at the heart of everything you said is you have to have a canonical data model. And constructing that and understanding, having the semantic understanding to even achieve that is by far the hardest problem. The problem of getting data out of source X and into either a virtual or a materialized view of that data is not the hard part.
So I agree. And we have identified, or I think we've identified the way where we're being successful at that without having to create the canonical model you're saying, which is reversing the way how you traditionally think about the problem. So even in your traditional EDWs, you still have to come up with your entire enterprise schema. And that's one of the reasons why it takes so much time. Well, why are you doing that? Because you need to answer business questions. So what we have been tackling is saying, don't tell me that you need to integrate all these databases. Tell me more, what are the problems what are the questions that you need to get answered? So we start with, give me a list of questions. 10, 5, 1. What is the most difficult or hardest question that you need to answer? And we start defining that canonical target model to represent that particular question. And then technically, that's where you actually start having the socialization at a very focused level. So the example I was giving you, the e-commerce, that's somebody they have tens of databases to integrate. But we said, let's just start with the question. And their basic question is, how many orders are we making every day? Because even in one database, they have 2,000 tables, right? The semantic problem is even with respect to one database. So with that, we actually go into the hallway saying, what is an order for you? Oh, it's for this. Where is this in the database? It's over here. Where's an order for you? It's over here. So you start asking the question, and you start then building that canonical model, the target model, little by little. And in our experience, we've had short experience, I have to say, but we've been having success with that. And it's really exciting because people realize I'm getting an answer to my question in weeks, if not days, where my traditional EDW, it would have taken 6 months and $1 million.
Just one comment. We typically found that we were in situations where we had 15 to 40 consumers of the same data. And so actually, I think you've just described the beginning of the problem of forming the canonical model. It's a very, very difficult problem, and it's a difficult problem to carry out dynamically over time. I'm not disagreeing with you about the incremental character of that, but I think it's those problems of data modeling are more central than the technology problems that some of the technology problems you addressed.
I agree, and I think actually what is needed is even methodology, even tools to manage that type of workflow is what we're realizing. That's what we're working on. And the moment you get people in the room and you talk about it, they realize they can't even agree. So it's not a technological problem. It's a social issue. It's a social problem. But people realize we need to figure this out. Otherwise, we won't be able to answer our business questions.
So thanks for your talk. But my question is, how could benchmarking help you in your business, or what would be the requirements from your business on a benchmarking organization like the one that is organizing this?
So the question is do I need to invest in a graph database or not? How do I know? So I need to be able to understand that if I need to do this, and this things, then I would like to have a formula saying if this and this and this, keep in a relational database. If this other stuff, you probably need a graph database. And actually, the other issue I hear a lot is, do I need an RDF database or a property graph database?
I don't feel answered.
Sorry?
I don't feel that you answered my question.
Well, I'll follow up on that. So using your own methodology, maybe you can help us find the 5 questions that are coming up in your line of work that you think a benchmark should represent.
So somebody gave a talk earlier right now saying, if my schema changes, I get a new database, right? So inserts of different types of databases, inserts of different types of data, right? New stuff that gets inserted. So imagine if you have your traditional, so if I keep my data in a database, I have a triple table, for example. So if data doesn't fit in my schema, I have to stick it in here, and I have to do queries. Up to what point does that fail? That if I had everything in a graph database, then performance would be better. That's one example of something.
Sounds like we need a new task force for data integration-based graph.
I mean,
Help us lead.
federation, and I know the other Hobbit project is doing it. It's federation benchmarks. That's the key one, right? To do this, I think that's crucial. We were talking about we need to have better optimizations for our federation and cache and all that stuff. I mean, that's a clear one to do. Having more of the navigation reachability types of queries. You guys are already doing that.
Yeah, but you're now maybe going back at Alistair's comment, or Alistair's comment. But so this is more the technological side of it, making technology faster, more efficient in doing federated queries. But the real, I mean, I also see, even if you have a virtualized situation where you actually do not have to do physical ETL. And you federate all this. There is still these rules that you have to create, which are actually the same. I mean, it doesn't really matter so much whether you're actually doing the ETL or you leave it virtual. In both cases, you have to write the ETL scripts. In your case, the ETL scripts are not called ETL scripts, but they are called OWL rules.
Oh, it's the clarity, which is the difference. That's the difference.
But they will also have to evolve, and they will, it will take a lot of effort to create them and to maintain them as well. So the problem is not only, well, this physical, but it's actually.
Yeah, I don't know if you guys would be interested. I think that's probably out of the scope, but that's something I find very interesting. In particular, because we now have the mappings that represent at a declarative level, the mappings really show me how things are being integrated. And at the end, I get a number, and the CEO says, I don't believe that number. And you can trace it back all the way down to the province. You know what, this comes from this calculation from these databases, and oh, by the way, John did it, and Mary was the one who authorized the change of that mapping. You want to go down to that. And all of that is a graph.
Okay.
Mappings are in a graph. The data, the schema is a graph. So, and that's why it's so cool that you have the data in the minute is all as a graph. So that's why I'm really excited about graphs. All right, thank you.
Thank you.